Hello. In this video, we'll provide a brief introduction to FHinfinity, the next generation of process furnace simulators. What makes FHinfinity unique compared to other tools on the market? It has been developed over the past 20 years specifically as an engineering tool, designed not just for simulation, but for actual furnace design and troubleshooting operational issues. To demonstrate this, we'll be simulating a cylindrical furnace in its base configuration. Keep in mind, however, that FHinfinity supports a wide variety of geometries beyond just this standard setup. To keep things concise and move quickly, we've pre-filled the input data. First, let's look at the firebox arrangement page. Here, you'll notice the live help panel on the side, which provides instant details on each parameter. As you can see, we've configured a top-fired arrangement with 6 burners. Next, we move to the coil layout. This furnace consists of 4 passes, with each pass containing 20 tubes. Moving on to the convection section, this page defines the geometry and the tube bank configurations. Moving on to the stack layout, you can see we've defined a simple stack with sloped bridging. The software allows you to easily adjust parameters like stack height, diameter, and even ambient conditions for draft calculations. Next, in the tubes data section, we have detailed specifications for both firebox and convection tubes. You can define everything from tube dimensions and materials to spacing. Notice how easy it is to switch between different tube banks. In the Convection Tube Types tab, we specify whether the tubes are bare or finned. Here, we've selected bare tubes for this simulation. Then, we have the coke and fouling page, where you can account for fouling factors on both the gas and process sides to ensure realistic long-term performance predictions. Under ambient and heat loss, we set the environmental conditions, like wind speed and temperature, and define heat loss percentages for the firebox and convection sections. Finally, let's look at the process streams. Here, we define the feed streams entering the heater. As you can see, we can input mass flow rates, inlet temperatures, pressures, and even fouling factors directly here. This level of detail ensures our simulation matches real-world operating conditions precisely. For each process fluid, thermophysical properties must be entered via the heat curve table. After inputting the data, you can plot and verify the curve for any parameter, such as density, viscosity, or enthalpy, to ensure accuracy before running the simulation. After defining the process streams, we move to the Fuel tab. Here, we specify fuel type, in this case, fuel gas only along with its composition, temperature, and flow rate. Before running the simulation, notice how the software instantly generates a fully scaled 3D model of the furnace, giving you a precise visual representation of the entire geometry. Now let's run the simulation. Clicking Run initiates the solver, which performs heat balance calculations across all sections. You can monitor progress in real time via the run log at the bottom. It shows iteration status and convergence metrics. Once complete, a warning appears. Don't worry, it's just informational. The results are displayed instantly. Simultaneously, the live 3D schematic renders the full heater geometry, firebox, convection section, stack, all color-coded by temperature for intuitive visualization. You can rotate, zoom, or isolate components. Here, we're viewing only the firebox tubes, then switching to show burners and convection banks. This interactive 3D view helps engineers quickly spot hotspots or flow imbalances. Back in the main window, under Output Data Generator, we can export detailed reports. First, let's generate the heater datasheet. It includes process conditions, mechanical design data, coil arrangement, and extended surface specs, all formatted per API standards. Next, the burner datasheet listing burner type, capacity, ignition method, emissions limits, and fuel characteristics. These sheets are ready for vendor quoting or internal review. We can also take a snapshot here to save the current model state, allowing us to easily revert to this version if we make changes later. After running the model, we can analyze the heater using our advanced diagnostic tool, Dr. Heater. This module performs a comprehensive technical validation. The system generates 3 types of flags: notes, cautions, and alarms. As you can see here, for this specific model, it has flagged issues like undersized burners, high flue gas velocity, and slug flow regimes, providing actionable feedback before finalizing the design. Let's go back to the model output data. In the charts panel, we can plot key parameters. First, we'll look at the flow regime profile, followed by the process side linear velocity profile, and finally, peak heat flux versus mean tube skin temperature. The sharp rise in the radiant section confirms the expected thermal loading. Let's take a look at the categorized reports. For deeper insight, we can generate detailed hydraulic and draft reports. First, the process side hydraulic report. This report details pressure drop, velocity, and flow regime for each tube row. Critical data for avoiding erosion or vibration issues. Next, we have the heater draft report. This breaks down the draft distribution from the burner level to the stack top, ensuring proper natural draft operation. Finally, the heat balance report summarizes overall efficiency, fuel input, heat absorbed, losses, and error margin. In this case, thermal efficiency is 73%, with minimal heat balance error, confirming model accuracy. All reports can be exported as PDFs, clean, branded, and fully editable. Whether for client delivery, archival, or regulatory compliance, FHinfinity delivers documentation that matches engineering rigor.